So in our questions that we're going to go through, start again. So in this video, we're going to do redox titrations, and we're going to show you a couple of questions. The first question is like this. You've got to find the formula of copper sulfate, hydrated copper sulfate, and we're going to find out what this X is here. Carries out a titration with thiosulfate. Thiosulfate is this thing down here, okay? And we're given the titration, the amount of thiosulfate there, or the concentration of thiosulfate there. A weighed sample of this is dissolved in water made up to 250, so there's a dilution thing there because we only use 25. Okay, and that is followed by an excess of potassium iodide. So basically the potassium iodide is being added to this, okay, to the copper, and we get this brown iodine colour, okay, and copper iodide, which is white. Two together makes this kind of like pale straw, kind of like pooey coloured liquid, which you might see if you do this in the lab. The blue copper sulfate is over there, okay, and you can see all these colours, and you can see it coming out now in the video on the right, and you can see it's that pooey kind of colour. I talked about pale straw type thing, okay, you see it quite clearly as I add the excess iodide there, okay, not the most pleasant of looking things. Now the resulting mixture is titrated, so we take that and we will titrate it with a sodium thiosulfate. So what I'm going to do now, okay, after I've given that a good shake and shown you the poo colour, okay, and you can see here, so before I go on, can you see here the white has just settled down, so there's all your white copper iodide at the bottom in your brown solution of the iodide as well. But let's put this all over to the side and we get rid of anything we don't need. So in the question you're also given this data that is down here and this data that's here. So you can get the mass of the hydrated copper sulfate in the first place. So this is where you can get the mass of that. Then you've got the titers, and remember we only use titers within 0.1, so stop the video and try and do it yourself. Okay, and we can see here that the ones that were in 0.1 is 21.8 and 21.7, so the average is going to be 21.75. So before we do that, let's do a question that was in, and this is an actual exam question we're talking about now. In step 2, why is an excess of potassium iodide added? So you add an excess of potassium iodide, okay. Now that potassium iodide means that all the copper, okay, is made, and which means that it is used up, and therefore that means that all the iodine is formed. See, we have got copper here, so we want to ensure all of this is used up, and so this converts all of this iodide into iodine, and we get all the resulting iodine we need for the titration. So everything is converted, okay, and that's why we do it. Now, next thing is, at the end point of the titration is approached, the student adds a solution to accurately detect the endpoint. State the solution and explain the colour change observed at the endpoint. This is so common, so utterly common, right? That is something you have to remember. So at the endpoint of this, we have your iodine, and your iodine can form a blue-black colour with starch. It forms a blue-black colour. So at the end, we add it at the end because it's easier to see, but at the end, we add starch. The starch forms a blue-black complex with the iodine, okay, and then it goes to colourless because what happens is you use up all the iodine, so you've got none of this blue-black complex left. That means all the iodine has reacted, okay, and that's a very common exam question for you there. Next one, we're just going to the main part of the question now. The main part is determine that formula. So let's have a look at first of all, the titer I mentioned earlier, 21.75 and 21.7 and 0.02175 decimeters. We have got thiosulfate here, and we've taken the concentration and times it by our volume. So concentration times volume equals number of moles of the thiosulfate. Number of moles of thiosulfate, hard thing to say, looks like this. Okay, and then what we can do is we do a divide by 2. Now I'm going to talk about this in a bit more detail. So if you go here, okay, you have got, on here you've got the number of moles of thiosulfate, which is here. You want to know the number of moles of the iodine, okay, because the iodine connects you to the previous equation. So you divide that by 2. That gives you the number of moles of your iodine. Now depending on what numbers are here, you don't change that amount of of your iodine in this case, it's nice because the iodine is 1 here and 1 here. But if it was 2 here, you still wouldn't change that amount of iodine. The iodine is still going to be 1.305 times 10 to the minus 3, 1.305 times 10 to the minus 3 here. Now, from that point, to get back to the copper, you times it by 2 again, okay, which takes it back to the original number. So I've shown you that we divide by 2 to get to the iodine, and then we times by 2 to go back to 2Cu2 plus, okay, to get this final answer. This final answer, okay, is the same as the original. So you can cut that out and just go straight to it if you want, if you understand it. Okay, anyway, so that gives you the number of moles of your copper. So let's make ourselves some space. Okay, we've got the mass readings over there. We're going to find out what our mass of A is. So our mass of A is 5.6. Hopefully you've done this. Have your calculator out. Do this. Then from this point, number of moles of copper in 250 centimetres, have to times by 10 because the original one was 25, if you remember over here. Dilution factor, very common in these types of things. We've got 2.61 times 10 to the minus 2. And then all we do is the molecular mass, and we calculate the molecular mass, is the mass divided by the moles. Okay, so the moles is what we've got up here. The mass is from the calculation over there, the mass of the weighing bottle minus the mass of the weighing bottle plus A, and it gives you a molecular mass. Now, if that's the case, the molecular mass is this and this. So what we do is we take the molecular mass of the copper sulfate away, which means we have the molecular mass of our water left behind. So 214.6 minus 159.6, and then we divide by 18, because 18 is the molecular mass of the water, and we get 3. So the overall formula is going to be CuSO4 dot, for the dative bond, 3H2O, and that's the first of our redox, and it's very common in that kind of way. So please get used to the process. The process will be exactly the same. So we start off with working out our number of moles. We then do the equations and find out what we have to times here and times there to get back to our original that we're trying to find out. Then we apply the dilution factor, and then we rearrange moles equals mass over mR to get our final answer. And this is a very, very common one. So we're going on to our next question, which is compound B is an iodate, salt of a group 1 metal. The iodate is IO3 minus, carries out titration to find out the formula of compound B. So compound B is dissolved in water, 1.55 grams in water, so you've got a mass. Makes up the solution to 250, okay, and the pipette's 25, so you've got dilution factor again there. And then gives 10 centimetres cubed of dilute sulfuric acid and an excess of potassium iodide. The iodate ions are reduced to iodine like below. So this is quite similar to the one we've just done. So you do this reaction here, okay, makes the iodine, okay, and then notice here the 3 and 1, 3 and 1, right? But the moles you calculate for iodine here are going to be the same as the moles that are here. You don't apply, you don't times it by 3, okay? We'll go through that as you go along. Okay, so we've got this, and it is asking us, going to make us find out what B is, basically. So here's our data, and let's put our titers in. Okay, so we've got our titers in, and then we have to look at those and just say, well, what is our average titer? Okay, so our average titer is going to be 23.80. You can see those two within 0.1 down there. Now we'll go through a few of the preamble questions. Describe and explain how the student should determine the endpoint of this accurately. So let's have a look at this. This is very similar as you've got before. Okay, notice you're making iodine, you're using up iodine. Okay, so do you remember from before what we do? And it's exactly the same. Add starch near the endpoint, because it doesn't work very well if you don't. And you go from blue to colours. All right, so exactly the same as before. So let's have a look at that now. Now determine the relative formula mass and formula of the group 1 iodate B. Okay, so we're going to form that. So we've got our average titer, we put it in decimeters. First thing we do, if you remember, is to work out the moles that we can, and we can work out the thiosulfate because we've been titrating it like we did before with thiosulfate. So let's work out the moles of thiosulfate. Got that, got the concentration from the question down here, okay, and then times it by our volume. We've got a number of moles of the thiosulfate from that point. Now, we've used this, so let's get rid of it. Okay, and then let's go to the next point. So, it's important to see if you can work it out. So we've got the number of moles of this to find, of this, and we need to find out the iodine, so divide by 2. Okay, and then that's our iodine here. We need to find out the iodate. Well, there's a ratio of 3 to 1 here. So we're going to divide by 2 to get iodine, and then divide by 3. Okay, so see what we've done? Divide by 2 and divide by 3. That gets us to our iodate, and there we have it. Very clever. We then times by 10 because of the dilution factor. Remember, we took 25 out of 250. Okay, and then we just do the same thing we did before. The MR of B is going to be your mass divided by your moles. We took our moles in, and then we got that. And if you do this, and this is the clever bit here, and there's a really, really clever bit in this, actually, which I will explain. Now, the fact is that and this isn't explaining the mark scheme, you see it. The fact is that this is the, if you look here, I have divided by the number of moles for B, okay? Because the number of moles of B is the same as the iodate. Okay, so we've said from the start that it's a group 1 iodate, which means the ratio of the metal to the iodate is 1 to 1, and the ratio of the molecule is 1 to 1 for the iodate. Okay, which means that this number of moles here of the iodate is actually the number of moles of B in the entire thing. If that's the number of moles of B, we can just say mass divided by the moles gives us our relative molecular mass of the whole thing. And if you take away iodate from this, you end up with a mass that proves that it is rubidium. And that is how you do this question. Very similar to the one before, and hopefully, if you're not sure, rewind the video, stop again, and try and do it yourself. So our third question is manganate titrations. Now, manganate titrations are to do with potassium manganate that reacts with other things like sulfite. So we want to find out how much sulfite is in the burgers. The burger is 525 grams down here, okay? And we want to make sure there's a maximum of 850 milligrams. So we need to do a conversion to milligrams at the end, okay? Taking the burger, extracted the sulfite, made it up to 250, took 25 out, and then titrated it with 0.01 and 12.6 centimetres cubed. We can convert that to decimeters, and we use that concentration, we times them together, and we'll get our number of moles of manganate, which we have here. Okay, so this is your moles of your manganate, and then what we need to do is apply the ratio 2 to 5. 2 to 5 is times that by 2.5, you get 5, which means you get the sulfite from the manganate, and then times it by 10 here, because of this dilution here, 25 to 250. Now, after that point, we need to know the mass of the thiosulfate. Now, this is a really clever bit. For every one of the sulfite, you'll get one of the sodium sulfite, which means that if I work out the number of moles using the number of moles of the sulfite, the number of moles of the sulfite is the same as the number of moles overall of the sodium sulfite. 1 mole of sodium sulfite contains 1 mole of sulfite, which means that number is the number of moles of sodium sulfite. Very clever. Now, if that's the case, we times it by the complete molecular mass. So it's moles times molecular mass gives you the mass of, and that's just manipulation of moles equals mass over MR. That gives you your mass of your sodium sulfite. Okay, and then all we do is try and apply it to the whole, to a kilo, because it's in 525 grams. So let's find out how many times 525 goes into a kilo, which is 1,000 grams, and then times our mass by it to bring it up. It gives you 0.7566, which I told you at the start that you're going to have to do a conversion to milligrams, or 1,000 milligrams in 1 gram. So this means that if you times it by 1,000, gives you 756.6 milligrams, which means you can eat the burger. Okay, because it is below the maximum of 850. Happy days. So this is our last question. We're going to talk about carrying out an experiment to determine the percentage of mass of copper in an ore. Okay, and so we're going to need a mass of the ore. Oh, here we have a mass of the ore. Okay, and we're going to need to know how much copper is in there in the first place. And we can use a titration. Titration is very similar to question 1, so I'm going to go quickly through this. Stop the video and read it if you want. Okay, so we form aqueous copper nitrate by adding nitric acid. So think at this point, what would you have, what would the copper be in, what would the ore be in if it formed copper nitrate, okay? So it's filter the mixture to remove the unreacted rock, neutralise the filtrate, add an excess of potassium iodide. You've done this before, add an excess of potassium iodide, okay? Precipitate copper iodide, and a solution of iodine. We've done before, and we'll hopefully you'll remember. I've left it out so that you have to remember it. Titrate the mixture from step 3 using thiosulfate, and here is your volume of the thiosulfate. So we know we've got to do moles. Again, tip with this is even if you don't understand what to do, just work out what you can and you'll get marks. So put that to the side. In step 1, they observe the bubbles of gas. That gives it away. Bubbles of gas. So which reaction does copper go through that produces bubbles of gas? Now you can get copper metal added to acid, which will give you gas H2. But we don't have copper metal, we've got a copper ore. So what with that? It could be a copper oxide. No, that creates water. Could be a copper carbonate. That produces carbon dioxide, which is bubbles of gas. So it must be copper carbonate. If we then do that, stop the video, try and write out the equation I'm just about to show you. That's copper carbonate plus nitric acid. Okay, so there you have it. And there's your copper nitrate plus nitric acid, CO2, H2O. Now, next, write our ionic equation, including the state symbols for the reaction in step 3. So we've got step 3. Now, you've already done this equation. It's already been in the last one. Okay, so I'm seeing if you remember it. Precipitate of copper iodide and a solution of iodine forms. Okay, so they're the products. So there we have it. So there's our copper, there's our iodide, and there's our copper iodide, and there's our iodine. And creates that brown colour that we saw earlier, white with this brown. Okay, if you ever want to practice it, balancing a redox equation, there's redox equations and redox balancing in the redox video. So there's a specific redox video where you can balance these kind of equations. This is one they like you to balance. Okay, but I won't go through it in this video because here it is. Now, from that point, if we then take this one down here, okay, and we now think about what is the suitable indicator for this. Well, this is very similar to the one we did before, okay? So we wait till the end, add starch, blue to colourless, to make sure all the iodine has reacted. So very common, very clear. I've gone through it 3 times, so please make sure you get it in the exam. Right, determine the percentage by mass, and this time we've got the percentage by mass, and we've got our equation here, because we're going to find out how much of copper we have, and remember we have to work back. So first of all, we do a number of moles of the thiosulfate. We took that from down there, got our number of moles, and then we have our number of moles of our copper. Now, I've shortcutted it here, but the number of moles of copper, let's go through it. So we have a number of moles here, okay, which gives us our iodine. Our iodine is our iodine up here. And then to go back to our copper, we have to times by 2. So we have to divide by 2 and then times by 2. So it's the same number. Okay, mass of the copper 2 plus in the ore is the mass of the copper times the number of moles in the ore, and you get the mass of the copper. So it wants you to tell you what is the mass of the copper, and so we've got it, okay? But it's a percentage by mass. So what we do is we take that, okay, and we take your mass divided by the total times by 100, and you get 1.35. And that is how you work out the copper in the copper ore. Now, last thing we'll go over is when the calculated percentage of the mass of the copper would be higher or lower or the same if the following changes were made. So have a look. Would the calculated percentage mass of copper be higher or lower or the same here? The potassium iodide was not in excess. Okay, not in excess. Okay, would it be less? Would it be more? Now the answer is it would be less, because less iodine turns into I2. If you're adding, remember you're adding iodide here, if you don't add all the iodide, okay, you won't convert all the copper. If you don't convert all the copper, you won't get the iodine, much iodine, okay, which means you get less iodine here, which means, okay, it'll tell you have less iodine, therefore less thiosulfate, therefore less copper by percentage. The burette readings were read from the top of the meniscus in step 4. So they're read from the top. So they're read from the top, and then the second reading you also read from the top. Well, isn't a burette a difference? Aren't you starting from the same point each time? So actually it makes, okay, sorry, top and top is the same as bottom and bottom. So it makes no difference whatsoever. So sorry, I should have added that in. So your classic answers to both of these are, if the potassium iodide was not in excess, you would get a lower and smaller titer. If the burette readings from the top of the meniscus, you would get no difference whatsoever. And that would be that. What further modifications should the student make to produce a more accurate value for the percentage by mass of copper in the ore? Okay, so what would they actually do? First of all, you'd repeat it and take mean concordant values. Take the mean of the concordant values. Now this is a common answer. So if you're ever asked this, what further modifications? Repeat it, take the mean using concordant values. Okay. Next thing in, percentage error reduction. Lower the concentration of the thiosulfate to increase the titer volume. If you've got a larger titer volume, your percentage error will be less. If you want to know more about percentage errors, and this is done in detail in the percentage error video or percentage uncertainty video that we've got at the start, which means also you could use a high resolution balance. All right, but just to remind you, here is your percentage uncertainty. Okay, and all you have to do to reduce uncertainty is to either increase your measurement or reduce your uncertainty. And you reduce your uncertainty with a balance, or you increase your measurement by lowering the concentration of something. And that's a classic way to do it. Again, if you want to go through it in more detail, that video on percentage uncertainty right at the start of the course is there. I hope this makes all of your Redox ones palatable and easy to understand. Please feel free to let me know in the comments.